Greetings, fellow chemists. We're going to work on problem number 7 in the practice problems for Module 6. This one says MgOH2 is the active ingredient in many laxatives. It can be made with the following reaction. It gives the reaction. If a laxative manufacturer has 3.6 times 10 to the 5th grams of Mg, or magnesium, how many grams of water must be used to have all of the Mg react to form MgOH2? So, we are looking at another problem where we need to go from grams of one thing to grams of another thing. And as we know pretty well right now, we can't go directly from grams of magnesium to grams of H2O. It's just not going to work that way because they have different masses and different sizes. There's no easy relationship. So we need to go from grams of one substance to moles of that substance, and then use the chemical reaction, the chemical equation, to get the moles of H2O so we can get the grams of H2O. It's a 3-step process, but ultimately it's not that difficult if you think through it and write it out. So let's go ahead and give it a shot. So I only wrote down the bits of information we really need. I have the chemical equation, and I have what we're starting with, and then what we're going to get. So this is dealing with limiting reactants a little bit, because we're simply trying to figure out how many grams of water must be used to have all of the magnesium react. So basically, the Mg here is our limiting reactant. We're going to have all of that react, and we can assume we have enough water to do any amount of combination with magnesium. So this problem is trying to solidify a little bit of information about limiting reactants. So here, if we're going to emphasize that point, this is our limiting reactant. So let's take a shot. If we go from 3.6 times 10 to the 5th grams of magnesium, we're trying to get moles. I'm sorry, that's not where I put that. We're canceling out grams, so we got to put grams on the bottom. So our relationship here, we need moles of magnesium to grams of magnesium. So we consult our periodic table, find magnesium. It's on the second column there. It's 24.3 grams per mole. Fortunately, this isn't a compound, so we don't need to add together a whole bunch of different atomic masses. We just have one to deal with. So 24.3 is what we're going to go with. 24.3, that's how many grams we need to make 1 mole of magnesium. And so we can go ahead and calculate this. So 3.6, and I'm just going to multiply out the 10 to the 5th first. So I get that this is really 360,000. I just find it to be easier sometimes to multiply that out so I don't get it mixed up with anything else later. And so now I'm going to divide that by 24.3 to get 14,814. Now the thing we need to watch out for is our significant figures. So our significant figures here, we had 2 significant figures, and we have 3, so we're going to have to get down to 2 here. I'll go ahead and do that now. So 15,000, or we could also write this as 1.5 times 10 to the 4th. That works the same as well. And that's what I'll stick with, I think. I'll write this down here at the bottom. 1.5 times 10 to the 4th moles of magnesium. So we move on to the next step. We already got moles of magnesium. We want to move from moles of magnesium to moles of H2O. So we'll keep on trucking through. Okay, there's our moles of Mg. We want to cancel that out with moles of Mg. Looks like MDES. That's not what I meant to write. Moles. Sure, I'll buy that. So, we want to get to moles of H2O. H2O is a compound. That's going to matter in our next step. But let's take a look at our relationship. So we have, for every 1 mole of magnesium, or for every 1 magnesium atom, we need 2 H2O molecules. And so our relationship here is 2 to 1. 2 goes with H2O. So now we can just go ahead and multiply this. You may already realize that this is going to be 3.0 times 10 to the 4th moles of H2O. If you didn't know how I did that, then you can figure it out on your own, but it's just how it works. So 3.0 times 10 to the 4th moles H2O. I'll go ahead and put that down here too, so I can save it just in case I need it again, which I will in the next step. All right, final step. We go from 3.0 times 10 to the 4th moles H2O. And remember, our last step is to go from moles of the second substance back up to grams. So we're canceling out moles H2O. And we're going to grams H2O. Now this is where I said H2O being a compound is going to be important for us to realize, because we're going to need to add up the atomic masses of the elements that make it up. So with H, we know that H is 1.01 grams per mole, and that's actually multiplied by 2, because we have 2 hydrogen elements or atoms in that molecule. If we look at O, 16.0 grams per mole, and that's just, there's just one of those. So if we multiply all this together, we're going to get 1.01 times 2. I'm going to add that to 16. And for H2O, we will get 18.02, but because of significant figures, mainly, how far this one goes out, we can only go out one place for that. So it's 18.0. And again, this is grams per mole. And so that's our conversion factor. So we need 18.0 grams to make 1 mole of H2O. And so we'll go ahead and multiply this. Again, if you want to multiply this out first, you're welcome to do that. I'm just going to do it in one step this time and show you how I work with that. So if I'm multiplying 3.0 times 18, I'm going to get 54. Really 54.0. Well, actually no, because this only had 2 significant figures. So 54 times 10 to the 4th. But that's not really how we write significant figures. In scientific notation, we would instead write it 5.4, and we add 1 there to show that we have a higher number. So it's actually 5.4 times 10 to the 5th. Whichever way you preferred, if you liked to do it the way I just did, you can do that. Just watch out for when you want to change the decimal point place. Or you can do it like I did initially for the first step, and that's to multiply the big number out ahead of time. However you want to do that, that's fine. But this is grams H2O. This is what we were trying to get from the beginning. So if we have 3.6 times 10 to the 5th grams of magnesium, we're going to need 5.4 times 10 to the fifth grams of H2O minimum to react with that. Now, if we're talking about limiting reactants here, since that's kind of the point of this problem, if we had more H2O, say we had like 6.0 times 10 to the fifth grams of H2O, we wouldn't get any more of our product because this magnesium, the amount we have, is what's limiting how much we can make. And so it doesn't matter how much water we added, we would get the same amount of our product. So we were just figuring out how much would react with the amount of magnesium we had. So that's kind of demonstrating the point of limiting reactants there. But that's how you do that problem.